Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello, Animesh. Thanks so much for joining us on the podcast. Such an honor to have you.
Thank you so much for inviting me. It's a pleasure and an honor to be here.
Thank you. So I'd like to ask you first how you would like to define yourself for the audience maybe first time listening to you.
I am Animesh Garg. I am currently an assistant professor at University of Toronto and Vector Institute, and I'm a research scientist at NVIDIA. I got a PhD from Berkeley in robot learning, and I spent time learning deep learning at Stanford. Primarily, I work on problems of machine learning and manipulation in robotics. A lot of the problems that we work on involve ideas from reinforcement learning, computer vision, recently ideas in deep learning, and the key questions that we are interested in is how can we have a robot that can do everything that a person can do with their hands.
So I'm curious to ask you firstly, maybe what are the maybe biggest question or hardest question you think in robotics and you still don't know an answer for?
Very interesting. I think there are big picture questions of understanding the nature of intelligence when motor control is included. So that's like a very what I would call metacognition level problem, where what I would say is we don't understand completely the nature of the problem itself. How do you specify the problem? Let me do a very simple example. I tell you to open a door or open a water bottle. Often what we don't understand is the meaning of the task. How do you specify the task? And without that, all of the what you would call downstream methods that exist would not work. Whether are you using control models, optimal control cell algorithms, or reinforcement learning algorithms, without the specification of this understanding that we call common sense, none of this exists. People study common sense, but the output or the outcome of those knowledge representation models is not actionable yet. So that's one big problem. Another problem that we have, particularly in robotics, as it connects to machine learning, is how can we make these systems learn with large amounts of data without forgetting? So a lot of the current machine learning is split into either supervised or learning or supervised learning style setups where you are operating on batch data sets. And the other one would be reinforcement learning, where you're doing interactive learning with an environment. The problem that we need to figure out as roboticists is how do we make use of past data that is only available to you in a batched setting? I have solved or I have opened many water bottles. How does it help me open this new water bottle? That's the question. And even more importantly, I can see people opening water bottles on YouTube. Can any of that help me open my water bottle?
Very interesting. Yeah. But I'm curious to ask you maybe what do you think is missing here so that we can achieve what you mentioned? Where do you think maybe the key points that we have to focus more or still don't have much consideration that could help in solving what you mentioned?
I think there are interesting challenges, technical challenges that my group is facing, but as a community, that I believe remain open. So the way I think about this is it's a four-part sort of problem that we need to understand. So let's use as a running example of what I believe needs to happen. So I always use this example of learning from YouTube videos as a North Star problem that can guide what technical challenges that we need to solve. And the North Star problem that I have is very easy to specify. I want my robot to cook me breakfast. I ask the robot to do something like, I want my eggs. I want a California omelet with cut avocados and well cooked omelet. Let's just say that, right? My robot goes to YouTube, searches for the recipe, and top 20 videos show up for something like this. What happens beyond that? Like, so this internet scale information retrieval is a problem we can solve. I'm not saying it's completely solved, but we can solve reliably, right? So with some information and language, you can get to meaningful descriptions. But beyond that, connecting it to the robot actually attempting it in my kitchen is just not solved, right? So the problem of, like, let's say, how do you infer what needs to happen? What is the recipe, first of all? What are the steps in the recipe? How do you know each of the steps is successful? So for example, that the recipe was something like grab eggs from the fridge, break eggs, mix eggs, then pour the mixture into a pan, heat pan, flip omelette, done, kind of thing. Let's just say that each of these steps actually have a done condition. That done condition is never specified. How does a robot actually build a classifier for when done? Right? When is it starting? When is it good to stop? Right? When it's cooking, what is a good time to call it cooked? Right? And now you can argue, oh, but we can train it with data. But where is the data going to come from? How does it do this for such large set of actions? Right? There's like a very broad set of actions that needs to happen. So now this brings us to, like, what technical problems? From a top-down perspective, first technical problem me and my group are interested in is exactly this problem of video understanding. To be very precise, not video understanding from a information retrieval perspective, but video understanding from an embodied intelligence perspective for fine-grained action recognition. What does it mean to open a door, open a laptop? What does it mean to break an egg? What happens or what changes are happening in the world, so that when an actor is attempting to do this, they can imitate. So that's number one. Number two is what I call 3D understanding. So far, all of these things are assuming image data, but often understanding objects from a 3D perspective. So this is yet again slightly different from a lot of 3D understanding in vision, but understanding 3D objects is important. I can ask you, for example, this is an object. Can you use this as a hammer? Many people might say, no, this is a computer mouse, but I can argue I can use this as a hammer. So then this basically means that you have an understanding of the shape and the task. So the first problem understanding videos was what needs to happen, right? The second problem is, now given an object and a scene, a problem instance, how are you going to do this? If you don't understand the what, you will not be able to adapt the how. The third part of the problem is, how are you going to learn to do this? This is where a lot of the focus, I believe, should be on methods like batch reinforcement learning, or what is recently being called offline reinforcement learning, or imitation learning. In principle, you can have a lot of data, either from your own experiences or from other other robots' experiences. And all of this data is, or may not be, from this particular problem instance, but you should be able to draw something from this data. So that's like the third part of the problem, right? So it's like, just to repeat, the first part of the problem was what, the second part of the problem was how, the third part of the problem is how to learn this from existing data. And finally, the problem is, so far I've only talked about like the high level problem spaces, but the mechanics of it will also come into play. And the mechanics is, when you talk about learning, it's not that some naive machine learning model will be able to do all of this. This has not been the case in computer vision, not has been the case in natural language processing. And I don't suspect that this would be the case in reinforcement learning for robotics either. Now, what are these abstractions and model architectures and priors that will help? Inductive biases. So in that case, I believe there needs to be two particular kinds of inductive biases. One is causality. So you can build causal models for either the dynamics or the value function in reinforcement learning that is doing credit assignment. Uh, so an example can be obvious things of causality is dynamics, where you can basically say, if I understand the understanding of causal examples where, like, if I tap the egg, it breaks kind of thing, then I can plan for such actions that will result in breaking the egg if I'm attempting to break the egg. The other thing is value function based causality. So, in the sense that if the omelette is not tasting good because it was not cooked properly, then the thing that you did long ago, which was mixing the eggs, if you did not mix them properly, then whatever you do after is not going to be good, right? So then it's causality from value function perspective, where you are saying that it's not good right now because you did not mix it properly. This is not an immediate action relation. So that's also causality, right? You're basically saying instead of dynamics, you're doing this in value function spaces. So that's one kind of what you would call structured inductive biases that we do not yet have in our reinforcement learning or decision making paradigm. And then the other kind of inductive biases are architectural kind of inductive biases, where uh, we need to bring ideas together from geometric deep learning and manifold learning into robotics. This again shows up in representations. So the objects that you're operating over, let's say input objects, 3D inputs, point clouds, or or let's say RGBD inputs, they need to, how should these models be processed? Uh, so that's one place where geometric deep learning comes into play. Another place where geometric deep learning also comes into play is uh, topological solutions and ordering over topological solutions. Let's say you can solve this problem. Let's say I can stir with my left hand and right hand. Which one should I do? Perhaps either of them are fair game. I can keep them around both, right? So when you have topological structure or any sort of non-Euclidean structure in the data or the space of policy parameters and weights, then you need special structures to be able to handle that. So yeah, so I think it was a long answer to your question of what are the challenges. I can repeat that in like one line. We need to understand what needs to happen in the world. Then we need to contextualize how will I achieve this with the set of tools that I have in front of me. Then I have to see how can I actually leverage all of my prior knowledge in doing so. And then finally, the fourth point would be what machine learning models would enable me to achieve this.
Interesting, yeah. But coming back to your work about how we can this kind of designing generalizable autonomy, and it comes to uncertain environment. For example, you mentioned the kitchen example. So how do you see this kind of achieving this kind of continual learning? You mentioned at the beginning to learn from the past data, and how do you see the approaches so far towards this kind of continual learning to uncertainty in environment?
That's actually also a very, very hard problem to solve practically. Uh, Uncertainty comes up in many ways, first of all. Before we sort of talk about how to solve uncertainty, let's understand the nature of uncertainty itself. Uh, Uncertainty is uh, the problem or the domain itself is uncertain, right? So let's say you cook eggs, and the way eggs get cooked is a stochastic process. You cannot exactly mix things, or you're mixing things is a stochastic process, and you don't have exact control. It's not like putting block on block kind of thing. So the world itself has stochasticity, even though you are trying very hard to fix this. The other is you don't know how to do this. So, as in, the model is uncertain, the world is fair enough, right? Often we talk about uncertainty in observation or model space, but we also need to talk about uncertainty in dynamics, or uncertainty in uh, inherent in the environment. So there are formal words for these kind of uncertainties, but an easy way to remember is um, uncertainty in the sense estimation. If you are trying to do this and you just don't know, versus uncertainty inherent in the environment, there is no way to know, right? Okay. Now coming back to your problem of how do we talk about generalization when environment will have uncertainty invariably? So in that case, let's assume first the easy case, which is estimation uncertainty. In those cases, we need better representations for generalization. So let's talk about uncertainty in dynamics, simple things. I'm trying to crack eggs, or I'm trying to whip a mixture. Maybe mixing eggs is much easier than mixing, let's say, a cake batter, right? Because dynamics is different, right? uh, if you have a policy representation uh, with the correct models of control, let's say compliant control, you don't need explicit estimation of those things to achieve the goal. And the goal is homogeneous mixture, right? So uh, basically, representations of goal, action space, and controller can allow you to handle uncertainty of estimation where you can get around actually estimating it perfectly. You could always argue that yes, I with some active inference I can figure out what the actual viscosity of the cake batter is, but then what's the point? It's not required. Okay, right? So you can get around it with better algorithms. That's one way to do this. Second set is sometimes you will not be able to get around. It's just that that's the nature of things, right? Grabbing eggs. Uh, if you grab them too hard, you'll crush them in your hand. If you grab them too soft, they'll probably drop. So you need to be perfect on that. Or of course, I'm using this as a running example. This happens everywhere. Uh, so in those cases, you need better algorithms that can model this uncertainty explicitly. So you can argue that I don't know, but I know that I don't know. uh, right? So by saying that, by modeling this uncertainty explicitly, you can have more risk-aware plans. Right? Okay. And then the third part is if you have good mechanisms, algorithmic mechanisms of uncertainty representation, and there are many models of uncertainty representation, we can get into that. Uh, then you can also try to capture the environmental uncertainty. If I have done this task 100 times and it's still sort of noisy, then I can argue that I am doing the right thing. It's just that the system has noise. So then, yet again, you can come up with risk-aware plans that can allow you to handle this uncertainty in a manner that is consistent with your, let's say, objective. Yeah.
So I'm just asking in that case because you mentioned about uncertainty here. When it comes to embedded intelligence, do you think this kind of uncertainty, the way we design the brain side and the body of the robot, the physical world to interact with that, how do you see this kind of maybe need more focus here? Do you think in the body of the robot is more important to when it comes to uncertainty and be adaptable?
That's always an ongoing question, particularly in people who do robot learning. How much of the problem can we solve with hardware? Uh, Broadly, it's a joint optimization problem, right? Your design of your hardware will capture certain problems, the morphology of the system that you use, the sensing ability that you have, let's say the sensitivity of your sensors, and then the fine-grained nature of your actuation or your control. Uh, Comes at a cost though, right? So the more sort of fine sensors and fine control you need, it probably needs at a cost of like accurate machining, better robots. At the same time, you can argue, or at least as a robot learning person, we can argue that hardware, very, very good hardware, is a mechanism to cheat. In the sense, cheat around algorithms. You can basically simplify algorithms and have solve the problem in hardware. But then one question we can ask is, would the system be truly generalizable? Can you have a generalizable solution in hardware? Often we can create what you would call automation style solutions in hardware. If there is a problem in a particular setting, I can find solutions in hardware that will solve that particular problem, right? If I'm not able to grasp the the pan correctly, I will change the design of the gripper to grasp pans. But now, what if I'm not grasping pans anymore and I'm grasping pens and paper, and I'm grasping other kitchen items like oranges and apples, right? So I cannot have 20 grippers, or I should not have 20 grippers. Right? Uh, so that's one thing. That said, there's still a lot of value in creating better hardware. Okay. Uh, Now the other part of the thing is, yes, we still need to solve these problems with what you would call slightly unreliable hardware and not hyper optimized for a particular task hardware. One thing I always find it interesting and important to say is one of the goal of robots, let's say a kitchen robot, is to not have 15 appliances. If I make the robot that only does panhandling, then all I have done is created a more interesting appliance.
Yeah, that's a very interesting point. But I'm curious to ask you about this kind of redundancy, the design, or simplicity. Let's say going to simplicity in design. So how do you see simplicity in design? So that we've mentioned at the beginning, taking a lot of data sometimes, it is really expensive sometimes, and that's challenges so far. But when you try to seek for simplicity, and also when you try to consider what are the trade-off you have so far, I don't know from your research group what kind of the trade-off you still can really avoid. But maybe first for simplicity, what do you mean about simplicity here?
Simplicity of design and algorithms. So,
Yeah.
simplicity, at least the way I think about, at least in hardware design, and let me give you an example of robot manipulation, is ideally, at least from a research vision perspective, we want to get to the most general point in hardware morphology so that I don't have to specify hardware for particular kind of tasks. I'm not saying that we have to do everything with the same morphology all the time, or it will truly be universal, right? Uh, so let me give you a for example, and then I'll give you an against example. So the for example goes basically like human hands, right? That there exists a morphology that can achieve a very broad range of tasks. In the same way, we can argue that we need to arrive at a robot morphology that is as generic as possible. Uh, we don't need to do all of the tasks in the world, but we do need better algorithms that will be able to use the same morphology for multiple things. It's like we don't want to hyper specialize things. We don't want a robot with a built-in screwdriver, and we are not looking for a Swiss Army knife with different heads, but we are actually looking for a single morphology. That's the simplicity in design, right? Elegance of multiple usage, and that comes through algorithms, right? You may not be able to do all of this thing without algorithms, right? Okay. At the same time, the against example is if you go to your kitchen, humans use tools all the time, right? Whether you are using a spatula because the pan is very hot and you cannot use it, or you are using a whisk because whisking it with your fingers may not work, or you are using a fork to poke something, or you are using a spoon or a ladle to grab something. In principle, all of these things could be done by hand, but you don't, right? Because it's inefficient or unhygienic or sometimes just implausible to do it, right? So now the question is, why would it be so bad for robots to have all of these tools that it can change to? Yes. So that again becomes a problem of, do you want to build the tool into the robot body,
Yeah.
or you want to impart the algorithmic mechanism such that a system, an embodied system, can use tools? I think I'm much more on the latter, that I'm not against the fact that a robot should not use tools, uh, because it is also not just a robotics problem, it is also an interesting problem from the perspective of nature of intelligence.
Yeah.
How did we come about arriving at designing these tools? How did we come about using these tools? Maybe the tools that the robot uses may not look the exact same way that we have, right? The tools for a robot, because the core or the generic morphology is not like a five-fingered hand. It doesn't have to be. Why does it? Uh, but I'm okay with it being able to use a generic set of tools. But you still have to be able to understand how to design those tools. We cannot say that I will design manually all of the tools for this robot. I think that is where it becomes um, an over engineered solution. So that's what I would call simplicity. So the understanding of what a tool means and how to use it is something that is morphology specific. A tool for, let's say, a baby, uh, a dog, a left-handed person, a right-handed person, and a robot may all be different, right? Because of the underlying morphology and, let's say, constraints of their kinematics and dynamics.
Yeah, that's very interesting. And I'm just as curious, as you mentioned, maybe for the tools, it could be new kind of tools, and I don't know how do you see that kind of pushing the limit of design or the fitness of the robot at the environment. Clearly, that we are human, we have limited fitnesses as we design, but when you try to see inspiration or what already we have in nature, and you mentioned that we can come up with tools we never used before. Can you give more concrete example, maybe from design perspective, what could be differently from what we use as a human as well? For example, the kitchen, yeah, for contact handling and with these new tools, how?
Let's think of a very simple example. A lot of our tools are often designed for power grips or precision grips, because those are the two kinds of grasp mechanisms that we use very regularly in our use cases. So let's say I use a pen. A pen is often held like this, right? I'm not saying this is the only grasp, but usually some sort of precision grasp is used. Uh, if I was using a pen for force, then I will hold it in power grasp mode, right? Now, if you think of like the morphology of design, a lot of your tools, spoons, ladles, will have handles which allow you to have this power grasp, right? So whether it's a spoon or a screwdriver or something like that. Now let's think of a robot with two fingers. Power grasp is not actually a thing that is available, right? Uh, if things are round, it cannot grasp it and apply force here because it will always be getting out. Like perhaps things will be flat here so that it can grab it and it doesn't rotate in place. Perhaps it will have grooves, so applying torque with is possible. Now the same thing with three fingers may be different, right? So the morphology of your system decides that what tools do you need that will work. Same goes for like another thing in robot that is different from people. People don't have continuously rotating wrists, right? So a lot of the tools we create are never designed for this. Like if we create a screwdriver, we do this. If we create uh, if we create a these sort of like rotational tools, often you notice that because of our limited rotation, they are never required. Like opening a water bottle, right, or something. But think of like robots. Robots can have continuous rotations. So opening a nut is grabbing it once and then just rotating. No grab, no grab hold rotate kind of thing, right? So some things morphologically are easier for robots than are for people. Uh, so the tools that you anticipate will be built will be slightly different for robots as well.
That's
But
interesting.
a lot of it has to do. I think I want to bring the focus of the conversation to algorithms. We can only design such tools when we understand how to solve the problem. Right? You can argue that what came the first, the tool or the algorithm, and I would argue that the algorithm came first, then the tool. So hardware does not come first. Understanding of how I'm going to solve the problem comes first. Then I fashion a tool. A lot of the time, right now, hardware is assumed to be a given. No,
Right.
right? You start with the hardware morphology. Someone who is working on robotics research for design and kinematics will design this, like saying this is how we will solve this, right? And then a lot of like algorithm people will use that and just like work with that, right?
Yeah.
But I would argue a lot of design doesn't happen, at least in nature, that way. You understand that this is what I go back to the original problem. You first understand what needs to happen in the environment, in a ghost environment, right? If I want to pour into cup, you need to understand that the can needs to be turned over into the cup, right? How you do this, whether I do this, a child does it, a left-handed person does it, or a dog does it, it may be different. The dog may grab it from the mouth. It could still be able to achieve the same task, right? So you first understand what needs to happen in the environment in an agent-free setting. Then you design a tool that will allow you to maximize your, um, let's say, ability to achieve the same task.
That's interesting. Yeah. But maybe a quick question here about the approach of solving a problem, because that's very important point about research. Sometimes it's uncertain. We don't know most of answers, but the way you approach asking the right question and figuring out the right solution, or maybe the solution could really lead to the answer. What could be strategy you think? And because clearly there's different approaches here and different way of thinking. But how do you see this kind of, yeah, from your experiences, the different way of thinking, where it come from, and where we can make unified effort to reach the right answer that we still don't have, or maybe in the way to full answer for that? Yeah.
I think just for I can speak for robot manipulation rather than generically research. That's too broad of a question to be answered here. Uh, you do have to scope your problem. You are absolutely right. Right, you cannot solve the whole problem all at once. You have to assume what experiments can you actually practically run, uh, what things are viable, and both from computational, economic, and sort of just the perspective of like feasibility. That said, it is important to have, uh, I would say, a philosophy in of research in this space. So let's say my philosophy in this space would be along the argument that we are out to build better manipulation systems, or systems that can do a wide range of manipulation tasks for two purposes. One, of course, we want to build the technology to be able to solve these tasks so that in a short run, in the 5 to 10 year understanding, we can actually build transformative solutions that can transition to places where these technologies can be used. But at the same time, the other objective is to understand the nature of intelligence, right? What does it mean to be intelligent uh, in a sense of dexterity? You could argue humans, among many of the organisms, are among the few living species that are as dexterous as they are, right? And you could even argue like that perhaps intelligence is because of dexterity, not dexterity is because of intelligence, right?
Yeah.
Uh, you have this very interesting morphology, and to be able to use this, you need to have the brain power, right?
Yeah.
Uh, right. So octopus is probably the only sort of argument that I can have is like equally dexterous, but then octopus are also assumed to be very intelligent in a very different manner as well. Now, coming back to your question, how do we go about picking our problems, or how do we going about scoping our problems? I think this is where, as a researcher, you will have multiple efforts. Some efforts would be more understanding the ecological pressures on morphology optimization. We do this. We had a paper where we said, if the task is given but morphology is not given, can you optimize for morphology simultaneously? It's a very sort of simulation only project, uh, but at the same time you also think about what would be generic morphologies that you can actually work with, and what sort of algorithms can you build with these kind of systems, and what tooling, particularly of the time. And I would say, for example, tooling would mean compute resources, tooling would mean simulation resources, that what I would call define uh, what sort of problems can we attempt today. Uh,
That's right.
an understanding of the ecosystem of tools is very important to be able to choose the right um scope of experiments, right? I can always say I want to build a robot that will, I don't know, uh, cook me lasagnas, and will be the sort of next best Gordon Ramsay. But probably I don't have a mechanism to train something like that, right? I don't have a simulator that can simulate all of the food items. I don't have the compute resources. I don't have even the morphology of the system. So then that problem is a pipe dream, not an active research project. So I think that's where understanding of the tools that you have at your disposal is very important in being able to make the right scoping of your research.
Good point. Yeah. But I'm curious in your research process. I don't know. Do you have witnessed any counterintuitive result? Because sometimes when we try to formulate the problem, but sometimes we don't understand why that happened and it was counterintuitive to you. I don't know, or maybe surprising.
Oh, yes, absolutely, all the time. Uh, I would even preface this. If we are honest researchers, we are evaluating our hypothesis. We are not out to prove our hypothesis. Uh, in the sense that as scientists, we come up with ideas and we try to see if they are good rather than we are out to prove that this is a good idea, right? It's a very different viewpoint, right? So in that sense, you can have a lot of ideas that made sense intuitively but don't actually practically work out. I can give you examples of multiple of these things. My own career, I think I'm glad that you asked. Like initially during my PhD, we were operating with projects. One of the projects was, and I'm going to give you like a couple of examples here where this was actually very counterintuitive. Was suturing used to be a very hard problem. It is still is automated suturing with robots. So when I was looking at this problem back in 2015, 2016, a few people had done suturing, but it was not very common. And we were trying to do it as general purpose as possible in the sense that the robot actually goes in, grabs the needle and does this. Other people had fixed the needle to the hand, so the only thing the robot hand is needles, nothing else, right? uh, okay, so then we tried this and we found exactly the kind of things you were mentioning, right? That the research process was the algorithms at the time that we had for state estimation, control, and planning were not sufficient to support the hypothesis that you can actually do the suturing. So then we had to basically step back and modify the hardware to reduce uncertainty in state estimation. We did that, and that allowed us to actually go from, let's say, 20% success to 90% success, right? And it's not that, oh, but the hardware change made it possible. You still needed all of the algorithms, it's just the system. All of the things are needed. No one piece is independently responsible. That was one thing that I learned here. Robotics is a systems issue much more often than you can argue that all of the success can be attributed to this one block. Okay. Uh, Another thing that I've also learned is yet again, right? In the last 5, 7 years, we have been working on a number of reinforcement learning algorithms. Very recently, we have been developing this framework called ISAC Gym. All ISAC Gym does is it takes the physics simulation to GPU. Now, in doing so, you can simulate physics steps very, very fast. So it's 3 orders of magnitude faster than um, let's say alternatives used in research. Okay, what does it change? So over the period of last few years, we started with many families of reinforcement learning algorithms. Let's say a policy search style algorithms, policy gradient methods. Maybe you have heard of that. Trust region policy optimization or proximal policy optimization or PPO, which are staple or very, very commonly used. Then a number of people started arguing, no, we needed better algorithms that are much more sample efficient, that use fewer data points. So then we started looking at on policy and off policy algorithms, which could use batch data, and so on and so forth. Right now, this time around, when we actually were able to build a better system where data was not as much of a problem, we found that in the last few years, the more efficient versions of the algorithms that people have been using are actually not working at all in this domain, right? The algorithms that work are still like 6-year-old PPO style algorithms, which are not sample efficient. But the fact that data is coming in so fast works, right? You do not need what you would call all of the fancy tricks in this domain. Yet another example was learning from real data. So a lot of robot learning or robot skill learning currently is split. Either you do real robot or you do simulation. A number of robotics experiments or algorithms have been talking about using batch or offline data. But most of that data is often generated by a pre-trained policy. So the experimental pipeline looks something like this. I train a policy to solve a task. However I train a policy, doesn't matter. Then I collect a lot of data with this policy. Then I see if I can learn a policy from this data set only, not interacting with the environment, and see if the performance of this new learned policy matches the expert policy. Right? This is, I would say, at this point, tens of papers, if not hundreds. Right? Now, we have been working on a project called Robotics, yet again, where what I would call rubber meets the road, where we worked a lot on creating and on our ability to collect dexterous, as in very complex tasks, uh, but real human data, where data actually comes in from humans. And the result was yet again very counterintuitive. We spent a year trying to get the best offline RL algorithms working, and we found that when data is actually coming from real people, not these algorithms, then none of these algorithms are actually working. The best working algorithms are very simple supervised learning or behavior cloning algorithms, which is very counterintuitive, because it's like saying that all of the things we have been doing are really not very useful for the problem that we really want to solve. They're solving this artificial problem, which is, according to me, sometimes sad. Oh, we have been spending so much time on problems that are, or algorithms that are not working. But at the same time, it's like so mind-blowingly sort of insightful that the fact that we need to, this is the problem we should be solving, right? We have suddenly discovered the true problem that we need to be solving. We don't need to create artificial problems. So that was an insight, right? Where in all of these cases, going in, I did not know that the algorithms that I was trying to make it work, because they had been published algorithms, they would fail so spectacularly. And the solution would be completely different. So I think this happens fairly often, and you need to keep an open mind.
That's very excellent. I think that's really excellent answer. But I'm curious to ask you in that case, because you mentioned something I think most of the time happening. What do you think the motivation that we go for the fancy solution? Of course, I'm not making here generalization. It depends on the nature of the problem, but you are not the first one to speak about that. Sometimes we go for a complex solution and it doesn't work. Why the motivation? And you have the most expertise in industry, or you work in Invade as well, and academia. And some people in the podcast say that they was counterintuitive, for example, them to go in industry and was solution very simple, not complicated. Do you think it's intrinsic nature that we want complex solution for sake of application? I'm not sure. What is the motivation, do you believe? Maybe there's other things. I don't know if you can answer that. Yeah.
So there are multiple ways to think about this, right? So as, let's say, a practitioner, if I'm a practitioner in a particular space, as majority of the people are for a lot of research output, right? What do I do? Like, what is my modus operandi? My modus operandi would be, I will look at the problem. I would do some literature survey, and I might find, let's say, 5 problems or 5 solution strategies. Usually, in reported literature, it may be that the complex solution will be reporting better performance than the simple solutions. Surprisingly, at times, much better performance. Now, as a practitioner, I have the trade-off. The trade-off is, should I use a simpler solution at n% performance, or should I use a more complex solution at 2n% performance? Now, if the gap is big enough in performance, then it might justify attempting this. Now, the problem happens when, first of all, the implementation process will be non-trivial, because it's a complex procedure by design. 2, the performance gap, or the marginal sort of gap that you are expecting to get, may be very little, right? Because nobody in the lab actually tested it on a real problem, right? So, and then that is where the disillusionment happens, where a complex solution that might need 3 to 6 months to implement and test may only give you 2 to 3% improvement, while something that you can do over a weekend will get you there very fast, right? So why bother? That's the usual argument. But at the same time, there's also, as you said, more of a, I wouldn't say inclination, but a psychological argument where if so many people have spent so much time doing something that has yielded this sophisticated solution, then it might actually be more useful. I just don't know about it, but it might be more useful. So you are basically inclined to trust the the experts, right? The experts are like other people who are writing these papers who you are not sort of coming from. So you are inclined to trust these experts. And I think that is where, as a research community, we need to improve in communication, in the sense that two things that need to be clarified is, if solutions have not been shown to scale, they are still valuable to be explored. I'm not saying we should not explore more complex and sophisticated models, but we should not be over promising. We should be very clear that any and all the results that have been shown to improve performance are on limited domains. And you should not extrapolate them to, let's say, large scale real life problems. We do not know what the behavior or the characterization of the problem solution would be. And that is the last part is usually missing, right? It's that extrapolation is rampant. And that is the problem where practitioners or non experts may get confused, right? And they may always prefer, or they may be inclined to use something that is coming from a named faculty or a named group or a named sort of research lab, uh, uh, just because it comes from them, right? Rather than like attempting something simple, because that's going against the flow.
Absolutely. Thanks so much for that. I think that's really great answer as well. And we need to think about that as well and the way we approach the problem. But come back to simulation, because I think the problem about sim to real gap. And sometimes we have this kind of, I think in the community, the plague of numerical instability in simulation. And sometimes we don't really capture the real dynamics happening when it comes to nonlinear system. And it's kind of, yeah, still a lot of things to do done here. But what are your thoughts about this physics engine, for example, we develop for robotics, and when it comes to your example you mentioned, uncertain environment with dynamics changing. So what do you think about this problem?
I think, first of all, it's not like a silver bullet blanket answer. Let me start with saying a lot of the progress that we have seen, especially in machine learning based techniques in robotics in the last 5 to 7 years, are perhaps due to the fact or in examples where simulation is possible. I'm not saying it's perfect, but is possible reasonably well. So if that is the case, often what happens is you can generate both visual data to train your visual state estimation models. You can train dynamics data to train your controllers or policies. You can train end-to-end models and so on and so forth. And then you can do very large scale sort of training and evaluation in simulation setups, and then try to transition this. Direct training on full real systems may not always be scalable from a broad set of tasks. Okay, so that's it. Now, your question was, simulation is not perfect. It will never be perfect. There will always be some things that will not be correct, right? We are not going to model all of the shear stresses at the level of, I don't know, cutting an apple or cooking an omelet, right? You're not going to actually model the processes that convert you this liquid into like a solid crepe, right? So the simulation will always be an approximation. The question remains, is the approximation good enough for the task you are attempting to do? That's one thing that you should always be aware of. Two, uh, even in those cases, even in the cases where we have a reasonably good approximation, it's not guaranteed or clear that this thing will work. One thing that I can argue, and this is the part where I would say I'm speculative, but I'm positive or optimistically speculative, that uh, in the next 5 to 8 years, we will see a lot of the progress in robotics algorithms being deployed in domains that we can actually simulate today. So a lot of the focus will not be on creating the next algorithm, but actually a lot of the focus will be in being able to simulate these tasks. And if you can do so in simulation, then the transfer will happen. The transfer may lose some performance, but it will still happen better than if you were to start from scratch. The problems in uncertainty of, let's say, state estimation, like visual recognition or visual understanding, or the problems in uncertainty of dynamics will both remain. Those things can be uh, solved through certain sets of algorithmic techniques. One set of algorithmic technique is domain randomization. So it's basically robust optimization during training. Another set of techniques is adaptive optimization or adaptive control, where you are adapting on the fly to the parameters that you're seeing. And these things can be applied either in optimal control style algorithms or in machine learning style algorithms, one and the same thing. Uh, like, let me give you an example. One thing we found, or at least everybody said so, is dynamic walking or legged walking was a very complicated task. The control is very high dimensional. It's very hard to simulate everything. The contacts are not soft. It's very hard to create slippage and so on and so forth, right? And that used to be what you would call conventional wisdom for over a decade, actually. Only recently we have gotten to a point where a number of people, I wouldn't say just us, we have shown this, but so have others at Google, at ETH, at Austin, at Michigan. A lot of the community, rather, has shown that if you can use your algorithmic ideas, whether optimal control or reinforcement learning, on a decently tuned simulator, then the sim to real actually works. There are mechanisms where this is fine. This is yet another example which was counterintuitive, because everybody thought this is so hard. Why would it simulate, right? Uh, Simulation is not perfect. You're only simulating hard objects while the world is soft. Like walking on carpet is not actually simulatable, right? Uh, so, uh, Yet, with clever choice of robust optimization and adaptive optimization, we were able to achieve non-trivial performance to a point where, at this point, you can argue that you can buy one of these robots and the controller works out of the box, right? So I think that that is yet again the same fallacy. We assume that this would be the case because that has been the conventional wisdom, without actually trying to build the system out. One of the things that has been, what I would say, a repeated lesson for me is robotics is a systems problem. It is science, but even more so, it is a systems problem. And we should be good at building systems and not shy away from executing the problem. I like to say this where, like, it's a one pointer takeaway. Often in robotics, you have to attempt to solve the duct tape version of the problem first to figure out what the real problem is.
So that's great. So since we close the end, I have a few questions. The first one, I don't know if you have moment of doubt through research. Yeah, how we deal with doubt, and yeah, I don't know if you have this kind of feeling or thoughts.
Absolutely, every day. How can you not? I believe nobody can have such conviction in their ideas that everything that they think of will work. I think if you say that you have such conviction, then I would actually doubt you. uh, Nobody knows the answers a priori ahead of time. The art of research is being able to take out or weed out bad ideas early on, while keep some good candidates that you can evaluate quickly. You don't, or more often than not, don't know the answer a priori. Now, often it happens that in some ideas you're evaluating, they take longer. You tried and they didn't work, and you don't know if you did something wrong, or is the idea is wrong, or the application domain is wrong, and it's unclear, right? It's completely. And now sometimes there is like this feeling among researchers that I've spent 6 months or a year or 2 years into this. Should I give up now and switch? Or should I continue pushing? I don't know how close I am. That's the. I think that's the art of research, right? It's just one of those things. Nobody knows when to stop,
Yeah.
and the best way to do this is to make research into your science, like science in the sense that try to be as quantitative about your progress as possible. Try to reevaluate the directions as often as possible. Try to question your methods as often as possible from a very independent mechanism rather than being emotional about them. Just because you thought of it first does not mean it is correct.
That's excellent. Yeah. And I don't know if you have maybe gained important quality. But I'm curious before that, the ego. Do you have ego when it comes to ideas sometimes? Because we have ego sometimes, yeah. It depends, but I don't know how we deal with ego.
I would like to say no, but I think that is not true. Almost all researchers would have to have some amount of ego. Uh,
Exactly.
Otherwise, you would not have conviction in your ideas. You will always
Mm.
be, meh, everything that I'm thinking is bad, and there is no way thinking about my own ideas. I'll just like follow someone else, right?
Mm.
Researchers are by design leaders, and leaders have to have conviction in themselves. Uh,
Yeah.
so yes, uh, yes, but I think instead of calling it ego, I would call it self-confidence,
Mm.
uh, self-belief. There is amount of self-belief and there is amount of self-doubt, uh, and I am cognizant that I have both at the same time, right?
Yeah.
uh, it's I'm not too proud of myself in that sense that I'm like pride is not the downfall, but at the same time I'm not comparing myself or to others all the time either. uh,
Mm.
you take things on their merit. uh, you learn to have a thick skin in general,
Yeah.
uh, and if you have ideas, you build a plan that is reasonable and viable, and not personally motivated. Uh, and if you make a plan after thinking about this, then you follow through with it, right? Whatever everybody says, and when you actually have evidence it's not working, it's not working. Rather than giving up because of emotional reasons, you give up because of empirical evidence.
Yeah.
If you have empirical evidence it's not working, then you accept it's not working and move on. If it is not, then you stay. So yeah, but
Six.
yes, you have to have some amount of conviction to stick around.
Yeah.
Research is almost always more about grit, and to have grit, you have to have self belief and conviction. You have to believe in yourself.
Absolutely. That's also an excellent point. And lastly, I don't know if you have received any advice or maybe something was changing your way of thinking and I don't know, in your research and stick to your mind kind of advice. Stick to your mind. I was changing your way of thinking.
So first of all, I have definitely received a lot of advice. I
Mm.
have enough self-doubt that I always seek out advisors all the time. Some of these advisors are people who I actually had the good fortune of working with, and some of them are just friends because I reached out to them or they reached out to me or we met through multiple sort of professional or personal reasons, uh, and they became advisors. There are many times, I think it's like multiple times I would have received advice. Many of times it would be game changing at the time of sort of hard career level decision making. It sometimes feels that you're operating with um, a lot of partial information. You don't know the future, you don't know how it's going to turn out, and it's very stressful. But I think I would say one piece of advice I received was during the end of my PhD and beginning of my postdoc. I was at the crossroads where I had many choices of accepting certain industry roles that were available at the time.
Mm.
Uh, and and I was completely and thoroughly confused, right? I had been a student all through my life. This was
Mm.
the first time I had been made an offer that was both technically interesting, that was monetarily very hard to refuse, um, and it was in the right location and everything checked out. But it was somehow just not in my heart of hearts, I felt that I wanted to try to attempt being a faculty. I'm not saying being a faculty is any better than being in industry or in other lines of, let's say, scientific vocation. It's just that at the time it felt that I wanted to attempt being that. I could always come back to this other job, and it was very hard for me at the time. I'm an immigrant in the U.S. It was very hard. It was like, oh, people work all their lives to get these kind of jobs, and it's like I've gotten it. How can I give it up? And I conferred with a number of my advisors, and I was extremely unsure, to be very honest, right? To a point where I even accepted the job. I
Yeah.
told the people that I will come, but I just like I could not make myself do it. And and towards the end, due to a combination of, let's say, fortunate circumstances, I got other opportunities to do postdoc, and both the postdoc advisor and my advisor at Berkeley uh, were able to convince me that I don't know the full picture yet. I'm too young. I
Yeah.
have to trust them that there will be newer, perhaps even better opportunities if I stick around. And that was very hard at the time, but that was life changing. I would say that was like inflection point. Had I taken the other path, I would not be as happy doing these kind of things today. I might be doing other things. I'm not saying what would have happened if, I don't know, but I'm very certain that that was one very sort of like important inflection point, and that wouldn't have happened if I were to just take my own decision. I needed
Yeah.
people to nod and prod me, and give me some sort of assurance that things will turn out okay. And it was at the time, of
Yeah.
course, a blind bet. It could have not turned out okay, but it did, and I'm very glad that it did the way it did.
That's very excellent. It's life, it's uncertainty, and sometimes we don't know really the full picture until it happened in a good way.
Yeah.
Often it's very hard for you to believe in the moment that they are working in your own benefit, or they are telling you to do something that you feel is not correct. But more often than not, they don't have anything to gain, and they have seen the world more than you do. So sometimes just trust in people. It's fine. You
Yeah.
don't have to be completely sort of self-obsessed. It's okay to
Yeah.
trust in people.
That's a great, Animesh. That's great. So thank you once again. I don't know if you have any final words you'd like to say. Do you have any final words you'd like to say?
So
I think first of all, thank you. You are doing a wonderful job creating this
thank you.
series. This is inspirational. I am genuinely honored to be a part
Thank
of this
you.
series. All of the other episodes for this podcast have been very illuminating for me, and for
Thank
everybody
you.
who is listening. I think the only thing I can say is uh, I'm glad that you chose to be in research, whether you are in academia or not. It's a hard choice to make. It's not always easy to be operating in this space, but nothing of interest is easy. A lot of the things that are things that you will be proud of potentially in the future will take sweat and blood at the time. So stick around. Please do, and I think it is through your brilliance and smarts only that can sort of the field prosper. So stick around.
It was really inspiring and very interesting what you do. Such an honor have you. Thank you.